No, what was actually funny is Brandon and Rebecca said, take the quiz like 2 months.
They and Matt apparently, like, Christine attached me to an email string that she was like sending my supervisor to Christine. Like, she was in Thursday.
All right, so here we are on the 27th of June, and we're starting our new unit, Unit 3, and we have 2 basic topics in Unit 3, which are going to take us through a significant amount of stuff, and then we go to Unit 4, and then we're all done. So we're halfway through right now. Note that we do not have school on Wednesday. It's the 4th of July, so no. My plan is to have the test graded and returned to you on Monday, but that doesn't always happen, so we'll find out between now and then. But we're going to, I mean, it's unfortunate that I have to talk so much today because you learn more when you talk than when I talk, it turns out. But we're going to be following the notes which are actually out there on Blackboard regarding Chapter 7 and the confidence interval. And I am videotaping this, so hopefully. Technically, I'm not using a videotape. I'm making a video. So that's how that works. But what we're talking about here, this concept of the confidence interval, when we say what is the importance of the confidence interval, and as it turns out, there are some people who say that this right here is all of statistics. So that if anybody is going to do statistics, there are some people who say this is the only thing you should do for statistics. And there's a debate out there about whether this is a good idea or not. As it turns out, there's somewhat of what they call a crisis in research these days, because people will produce something and they'll produce the research, and then somebody else tries to do the same thing and it doesn't work. So then you say, well, was that first thing actually a thing? Or was it just a random fluctuation kind of a thing? And so then by using confidence intervals, supposedly we're able to say it's a thing to this much. It's this much of a thing. Whereas in other kinds of research that you do, you don't know that. So then this is a way sometimes for us to say, what are we really saying when we're doing statistics? How much confidence, obviously, can we put into the things that we're doing? So then when we say it's an interval, we need to understand the difference between what's called a point estimate versus an interval estimate. And in order to illustrate this, I'm going to put this little dot right here. And I'm going to use this marker, and I'm going to stand right here, and I'm going to try and hit that dot with this marker. Do you think I can do that without looking?
No.
I missed. Okay. Now I'm going to use my bag. Do you think that I can hit this dot without looking?
No.
I did. All right, that worked. So does it make sense for us to use a single number to try and get an answer in statistics? The answer is no. If somebody were to ask you a question, does this medicine actually help children with their blood sugar? And if you said it lowers it 13 points, that's probably not the right answer. Because if you say to somebody, this thing does a thing and it does it to this amount, that's probably not the correct answer, because a dot cannot be actually found by hitting it with another dot. If you say, how much does this thing actually work? Does this actually happen? It's probably not a single number. A single number is not the best answer. So we try to avoid, in statistics, using the idea of a point estimate. We don't get a single number answer. We get an interval estimate. So if somebody were to say, does this medicine reduce the blood sugar? And you say, it does it somewhere between 8 and 18 points. Then you're like, that seems like more of a reasonable thing, okay? If you say it's between here and here, then that makes sense. There's tons of examples of this, okay? If somebody says, what's the temperature going to be tomorrow? And if you say it's going to be 93.7 degrees for a high, that's most likely wrong. But if you say it's going to be in the 90s, well, then you've got some room, right? Anytime that it would be in the 90s, you would be correct about it. And so why we're doing this is because our answers or our numbers are constantly changing. It makes better sense for us to say that the answer is an interval of numbers, not just one single number. So if somebody says something like, unemployment is at 7.8% or 2.3%, that's probably a wrong answer, because unemployment might be somewhere between 2 and 3%. So when you have something like this, and it happens all the time in the news, when people say, this is this much, it's most likely that the thing is not really that number. It's somewhere in that neighborhood, maybe. But the better option for us when we're talking about actually knowing what's happening, that's what statistics is about, knowing what's happening based on numbers, is to use an interval, not just a single number. Okay. Now, let's consider this thing. What is my lunch cost? If somebody were to ask the question, how much am I going to spend for lunch if I go out to eat? And I want a good interval estimate. How about this estimate? From $0 to $200. Is that a good answer? Why not, Nikki?
Too much of a range.
Okay, but is it correct?
Yeah.
All right, it's correct, but it's no good. Okay, it's giving us information, but it's not giving us good information. What if I said your lunch is going to cost from $8.20 to $8.30? Is that a good answer? Why not? Okay, it's more accurate though, isn't it? It's a lot more accurate than this. But it could be wrong, okay? So what do we have to do? We have to balance in between here. We have to say, I want to be right, but I'm not going to be right all the time. And so I have to consider the accuracy of my answer is going to be changed based on how right I want to be, okay? This is right 100% of the time, but it's not accurate. This is very accurate, but it's not going to be right very often either. So I have to somehow find a balance between those two things. And that's what a confidence interval is going to allow me to do. Now, it is important for you to understand what does the confidence interval actually do, and we're going to talk about the process of statistics. Somebody tell me, what's the process of statistics? Something we talked about right at the beginning.
Observation.
No.
Yeah, but you're going to-
No. Process of statistics. That's the purpose of it. I want the process of statistics. No, not exactly. It does have to do with those two things, but yes.
Is it to use a sample to understand the population?
To use a sample to understand the population, yes. Okay, we're going to use a sample to understand the population. It's not just that we have both of them. We do, but specifically then, when we say what happens with a confidence interval, a confidence interval uses a sample to measure the population. Let's say that I was interested in selling dog sweaters. I know they exist, I've seen them. Okay, a sweater for your dog, okay? If I ask every person here in the class, do you want a dog? I'd get a number, right? I'd get an answer. Does that tell me how many people in La Crosse own dogs? It does not, okay? So if I get a sample from you guys, if I want to sell you doggy sweaters, that's great information. But if I'm trying to get this in the whole city of La Crosse, it's not going to necessarily get me what I want. Knowing the sample is what I do when I make my observations. But knowing the population requires more of a longer process. I have to think more carefully about that. That's what the confidence interval will do. The confidence interval will take the information from the sample and it will tell me something about the population. Do I really care about this class dog ownership if I want to know the city dog ownership? Not really. What you're giving me is just one little piece of information. What I really want to know is what's true in the city of La Crosse. Same thing is true for any study that somebody does. Let's say we're talking about orange juice for children affecting their discipline problems. If I find that out for my little group, well, that might be great information, but I'm not going to publish that just for my little group. I want to know if it's true in general for kids or whatever. So what I'm trying to do is get little groups of people or little groups of whatevers, measure that information, and then say, can I say it's true about the big population group? The confidence interval will say that. It will talk to me about the population, not just about the sample. All right. Now, how are we going to actually do this? Well, we're going to use a couple of definitions here. And the first one is going to be this symbol right here. This is a Greek letter, and it's called alpha. It's the first Greek letter. It's where we get our alphabet from. Alpha, what we start with. And so when we say alpha, that's this symbol right here. It's not the funny looking A shape. It's not the fish thing. Okay, it's the word alpha. It's the Greek letter, first one. This is the small alpha. And the meaning of this thing is our chance of being wrong. So do we want alpha to be small? Yeah, it seems reasonable. We want a small chance of being wrong. So alpha is normally going to be a pretty small number. In fact, what we choose normally for alpha would be 0.05. Because we want it to be unusual, right? To be wrong? Okay. But there are also other choices. Sometimes we can take alpha to be 0.01. We could take alpha to be 0.10. We could pick it to be 0.02. Not very often, that does happen. Okay. So, knowing this thing about alpha, then that's going to describe for us our level of confidence. The level of confidence is going to be 1 minus alpha as a percent. So I look at something and I say, okay, I want to be relatively sure about a thing. So I'm going to pick an alpha value. And then I'm going to say, what's my confidence? So this is 0.05. What's 1 minus that? 0.95. How would I express that as a percent? 95%. So if alpha is 0.05, that means I have 95% confidence.
I have a question.
Sure.
What is that 1 minus the alpha? What's underneath it?
As a percent. Okay. So I have a level of confidence. It's 1 minus alpha, but I'm going to write it as a percent number. So what if I have an alpha of 0.01? How much confidence do I have in that? 99%. Okay, what if alpha is 0.1? %. And if it's 0.02, that would be 98%. Most of the time, we choose how much alpha is going to be. And most of the time, it's 0.05. So what we're saying here is I'm going to choose my probability of being correct to be high, my probability of being wrong as being low, and then that's going to determine the accuracy of my numbers. So I'm going to choose my amount of confidence. Then I'm going to go through a formula, and then that's going to give me a certain amount of accuracy. So generally what we want to say is you can't mess with your confidence partway through a problem. You're not supposed to start a problem and then say, oh, well, I've decided I'm not going to be that picky. Usually you're setting up your confidence for some reason, okay? Like if you're doing a marketing campaign, maybe you just need 90%. But if you're dealing with nuclear explosions, you want to be 99% or something, okay? So these are some definitions of how we're going to set this thing up. And so then I'm going to show you something that's in the textbook, and it's on page 367, so that you can keep track of this to know how it works, because it's going to be something that when you say, how do I understand the confidence interval? It's going to be important that you have a specific picture in mind. So I'm going to get to there here, hopefully. This is on page 367. Why are you not giving me what I want? There it is. Well, this thing says 366, but I think it's on 367, okay? So this is a picture of how confidence intervals work. Just like when I was hitting the thing with my book bag, I was pretty confident that I was going to hit the target, okay? But if I had used something, you know, like maybe my eraser or something like this, if I had gone to hit it like this, I would have been less confident, right? So what's going to happen is that whenever I do a confidence interval, I'm going to be trying to hit the population number. Right here. Here's the population number. But my confidence intervals, they go up and down, back and forth. So sometimes I'm going to hit my answer, sometimes I'm not. For example, in these confidence intervals, most of them did hit the target. This one didn't hit the target. So we're just trying to find something that works. And most of the time, it is going to work, but sometimes it won't. That's alpha. Sometimes it won't. This is how many times we would expect to miss the target. Our confidence would be how many times we expect to hit the target. We don't actually know the value for the population, but we're pretty sure it's within our interval. We can't be 100% sure, but we're going to try to be sure it's based on this. Okay? So having this idea, we're trying to hit a target with a wide interval, and sometimes we're going to miss it, sometimes we're going to hit it. That's what that's all about. So then, we need to do this. Specifically, we're going to do it with our 3 measurements that we can do. Confidence intervals for these 3 things. Proportions, means, and standard deviations. So I can use confidence intervals for these 3 different measurements that I'm trying to make. Oh my. Yeah. Well,
There's another one under the.
yeah, well, there's one over here. That's what was a little better, but not much. Because they used to have cloth that they would use on these things. And then somebody washed the board and oh well. Not as good as it could be, but.
Wow.
Okay, I erased the board. So, now there used to be some spray over here, but. All right. So, when we ask the question, how does this thing work? Now you do have, again, electronically, there is a formula and information sheet that's out there. So if we go to resources, important formulas and tables, this is where we are. So I'm going to put this up here, we're going to write it down, and then we're going to talk about what it is. The confidence interval for a proportion. So does it have just a Q in there? That's good. All right, I'll give you a minute to write that down. Oh, let me put parentheses. Now, when you look at this, you see those inequality symbols, right? The less than symbol. And you see the letter P is in between them. So what that means is that we're going to be looking for the answer that we're going to get when we ask the question, what is the confidence interval? The answer will look like this. It'll have the letter P, and it'll have a number on the side and a number on that side. That will be our interval, okay? So when somebody says, what's the confidence interval for the proportion, then this is what the answer is going to look like. Well, what is this thing right here? Might look relatively familiar. Okay. We called this before the general probability, right? Probability. It's also called the population proportion. So this would be a situation where we're saying, okay, how many people have ever played Yahtzee? This number that we're trying to find is the proportion or the percent in general of how many people have ever played Yahtzee. Okay? We don't know the number. And when we get done with this problem, we still won't know exactly what the number is, but we'll have an idea of where it is, somewhere between two different numbers. Okay? This is the general probability, the population proportion. We don't know the answer, but we're going to put it into an interval. So we think we know where it is, even though we're not quite sure. But what is this? This is P hat. It's not fat, okay, don't put it there. It's P hat. That, right? It's a P with a hat on it. What is P hat? P hat is called the sample proportion or the observed probability. So we don't know the general probability. We don't know the population proportion, but we're going to try to use the sample proportion in order to get this interval. And the actual population number is somewhere in that interval. At least we're pretty sure. Okay? Now, how do you find observed probabilities? How are we going to figure this out? Well, we're going to, just like what we did on the exam or whatever, we're going to have the number of observations divided by, the number of successes divided by the total number. Okay? So, let's see. How many of you have ever played Yahtzee? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? So 14. 3, 6, 9, 12, 15, 18, 21. Okay? So now let's make it easy. 14 out of 20. So what is my p hat in this situation? P hat is 14 out of 20. What's that as a decimal number? 0.7. Okay, so that's my p hat. Now, as it turns out, this sample size is too small. 20 people is not really enough to do this. So we're going to pretend that we did 140 out of 200. So I'm going to change this to 140 out of 200. So what I did in my pretend mind was that I talked to 200 people and I said, have you ever played Yahtzee? 70% or 0.7 is what I come up with, that proportion of the sample. Okay. Now, what's Q hat going to be? Well, Q hat is just 1 minus P hat. So what's that for this? 0.3. 0.3. Okay. So I'm getting there. I'm getting to the point where I can put things into my calculation. But there's a big problem. Well, first of all, there's a small problem. What's n? 200. Okay, so I talked to 200 people. Once again, n is the number of people I talked to, or my number of total observations. Okay. So far, I'm getting there. So p hat, recognize p hat comes from the sample. It's not the same as the general probability. I don't know what the general probability is. All I have is this information from my sample. I want to find the interval for that general probability. I don't know what it is right now. So I'm looking at this right here. And I say, well, what do I need else in this thing? I need this. But what does that actually tell me? This is the z-score for alpha divided by 2 in the tails. That symbol that I put up there, it has a z in it, and it has an alpha divided by 2, but it's not a multiplication problem. I'm not taking z times alpha or dividing it by 2. That's not the thing. Alpha divided by 2 is a label that I put onto the z. This part right here is not mathematically active, if you want to say it. This here is just a label. That part is telling me where to find the z-score. Okay? So in this problem, if I'm going to do a confidence interval, I have to know ahead of time what my alpha is. In order for me to do a confidence interval problem, we have to start by knowing it's this much confidence, so it's this much for alpha, and then we can go through and do the rest. Okay? So what we're going to need to make this happen then is we're going to have to decide what confidence we want, and then we're going to find the z-score for that situation. So what I'm looking at here is I've got 0 in the middle, and I have the tails on both ends. And I want alpha to be the total of both of those things. So I'm going to have an area of alpha divided by 2 on both sides here. And the question is, what z-score will I need in order to make that happen? I need a z-score to give me alpha over 2 set up like this. So, in order to make this work, I have to decide on a level. So let's pick a 95% confidence interval. If I want 95% confidence, then alpha has to be 0.05. Okay, we already did that. We made our little chart. 95% confidence means alpha is 0.05. Well, what's alpha divided by 2? That means you need to have 0.05 and divide it by 2. 0.025. Now, the nice part about this process is, once we do this one time, we're going to know the correct z-value for a 95% confidence interval. We only have to do this once, and then from there on, we will always know what the 0.05 or the 95% confidence, what that z-score is. So, we want to have 0.025 as an area. And we're going to take a look at that table then in order to make that happen. Now you have the copy of the table, all right? So I want you to take a look at your table so that you can find where this is going to be.
Table E or what table?
Table E, yes it is. I want to have an area of 0.025 in the tail. If I want 0.025 for an area in the tail, where am I going to go?
Negative 1.96.
Negative 1.96. If I look at negative 1.96, I've got an area of 0.025 in the tail. That's on the negative side. What about on the positive side? Are they the same on either side? Yes, they are. Z-scores are the same on either side. So yes, if I look at 1.96, that's 0.975, which is on the left, so that would be 0.025 on the right. Okay. Now, in my formula, you see the formula up on top here. The formula has a plus sign and a minus sign. So then I really don't need both of those numbers. I can just say 1.96 goes in on the left and 1.96 goes on the right.
Not negative.
Because this already has the negative sign. So I'm not going to put a negative in here. I'm just going to have minus 1.96. So when we find the number that we need, then we have to think about if this is negative 1.96 and this is positive 1.96, then that means 1.96 goes in both of these places. So I'm going to put that into my formula after the subtraction and after the addition. is going to be 1.96.
And we're using the 140 out of 200 numbers.
We're using the 140 out of 200 number as the p hat. Now, again, I just want to emphasize this to you. Now that we have this number, this 1.96, we don't have to go through this process with the z-scores. Whenever we do a 95% confidence interval in a situation, we know now it's 1.96. We don't have to keep looking it up and figuring it out. Okay? We know that 1.96 number now. We could do it again for 99. Sure, we could. Or we could do it for 98, or we could do it for 90%. Okay? We could do that. Or if your teacher was so inclined, your teacher would just tell you what those are. So it's not really necessary for you to look up z-scores on all these things. If you have them one time, then you have what you need. So where is that thing here? If I go to here.
I have a question.
Sure.
So when we're talking about the z-score and how we found the negative 1.96, is it just like always going to be the same positive number, or why? Because like when you look on the positive 1.96, that number doesn't make sense to me.
Okay, if I go to positive 1.96, that number is 0.9750. That is from here all the way to the left. So that would be this amount of area, 0.9750.
Okay.
But what I care about is what's in the table. If I take 1 minus 0.9750, I get 0.25.
Oh, okay.
That.
Okay.
All right.
I think I missed the second half of that explanation.
Okay. All right. So now that we know this number 1.96, and we have, for this particular situation, we know the p hat, the q hat, and the n. Now we need to put those numbers into our formula in order to get that confidence interval. But it's very important that you understand the order of operations. You do not find this number and then add or subtract 1.96, hit equals, and then multiply. Don't do that. Okay? What you have to do is have a separate calculation for what comes after the minus sign. You have to do this section. That's going to give you a number. And then you're going to take this minus that number, and you're going to have this plus that same thing. These are the same on either side. This thing, which comes after the minus sign, which also comes after the plus sign, that's called the margin of error. And we use a capital E for that number. So be careful when you're doing your calculations to understand the order of operations. You're going to want to do your calculation of the margin of error first. And then you're going to subtract it from p hat. That's one side. Add it to p hat. That's on the other side. Okay.
You could enter that whole thing into your calculator.
You can enter the whole thing into your calculator, but you have to be careful because when you take the square root, you have to have that whole thing in parentheses when you take the square root. Because if you just hit square root and then the first number, that's not good enough. You have to make sure that all three of those things are underneath the square root sign
How do you do that?
with the parentheses button. Square root, parenthesis. Then you put the numbers in and then hit parenthesis on the right. So what we have is 0.7 minus 1.96 times the square root of 0.7 times 0.3 divided by 200. That's going to be the left-hand side of our confidence interval. So you need to do that so that you can make sure that you know how to hit the right buttons on your calculator to make this work. 4 digits of accuracy is good, yes. Now, when we get to our answer, usually we only need 3 digits of accuracy when we get to our answer, but 4 is okay. And it is acceptable for you to just put all the numbers into your calculator and get them. It's also acceptable for you to find the margin of error separately and then do the subtracting and the adding.
Are you multiplying 0.7 minus 1.96 times the square root of that?
Oh, you so I did.
This right here has a multiplication here, a division here, and a square root. And this is a multiplication here.
Yeah.
Between that.
From
Yeah, okay,
This is a subtraction.
yes.
I could be.
After all this is done, this minus that. Okay?
Okay,
Or if you put it all into your calculator, it would look like this. 0.7, 1.96 times square root in parentheses of 0.7 times 0.3 less 200 right parentheses. If you want to put the whole thing in your calculator and get the answer, this is what you would do.
Otherwise, you would do 1.96 times the square root.
No, if you're not gonna do it that way, all right, then you've got to do this, multiplication and division. Get that number,
Okay.
take the square root of that number,
Yeah.
multiply by that number, and that gives you your margin of error. Then you would take p hat minus that, and p hat plus that.
But the way you just showed us prior to that, we can't start with 0.7 and might as well do 1.96 on and then minus it 1.7. Are you saying we can't enter the whole thing into our calculator?
You can enter the whole thing into your calculator.
The 0.7.
You have to include the 0.7 in order to get the entire answer. If you want to just do this, you could. And then take 0.7 minus this.
So you get the answer right in the whole thing.
Either way, you would get the correct answer.
Do we answer? I don't know, I just.
Okay, so you might want to check with your neighbor and see if your neighbor needs any help with this particular calculation.
What? Did we just switch numbers?
And then like when we're at the final answer, we do like this number
That's
plus
so
P.
Yes.
Yeah, 763.
I think you were right there, so.
Now, I don't know why this is, but I accept it. Human beings have certain characteristics. How important is the rounding? At the end of the problem, it doesn't matter, really. During the problem, you should not round things off very much at all. When you get to the end of the problem, you should get something really close to 0.636 and 0.764.
So once you go through all your math, go through this, find the square root, you get that.
But for whatever reason, people go ballistic and fly up into the sky with showers of sparks when I say, that's close enough. Okay, but it is.
Well, I would do this times this, but.
All right, so if you don't get these numbers, we need to fix this. Find out what's going on in order to not have the right answer.
Which is this number right here.
This is the confidence interval. This is the answer we get.
The difference.
Okay, so this has to happen because you're going to be doing a ton of this, and it's going to get a lot more complicated in about 15 minutes, or maybe 20 minutes. But for right now, you need to be able to make this happen right now.
You can hang on, and you can add this number and subtract it. And when we try to do and then just take 0.7 minus and plus this.
Okay, Danielle, you're getting in trouble there. Okay, tell me what you're doing, Danielle.
I got the first one. I was trying to figure out the second one, and I was gonna try and put it all in the calculator, like it was
Okay.
like that. But the first time I didn't do it that way, and I did it the first way where you like.
Okay, so if you're going to put it on your calculator, it's going to look exactly like this, only with a plus sign.
I know, but that's not what it came out to me. So
Okay, did you put in 0.7?
I'll try it again.
All right, plus 1.96 times
Yes.
square root parenthesis.
Oh, maybe that's where I'm.
Yeah, there you go, parenthesis. Right parenthesis.
What?
Yes, at the end, after you put in your left parenthesis, you have to put in the right parenthesis. Yeah.
Oh, yeah.
Oh, you do.
Now, some calculators actually put in a parenthesis after you hit a square root button. Some calculators don't. So I don't know which one you have. So I don't know what you're doing. You have to find out what you're doing and then make it work. If it works, we're good. Right?
But
It's divided. That's like 2. My goodness.
All right, so then the question is, what does this actually mean? What is the meaning of the confidence interval?
Okay. Wait.
The confidence interval is using a sample to measure something about a population. If I talk to 200 Western students, have I talked to all the Western students that exist? No. 200 would be a sample. if I find out that 70% of those students that I talked to have played Yahtzee, do I know exactly how many Western students have played Yahtzee? No, I don't. All I have is a sample number. My sample number was 70%, or 0.7. What is the actual value for all Western students? It's somewhere between 64 and 76%, based on that information.
Confidence interval would be in a percent?
Usually that's how it's set, yes. So that when we say, what is our actual proportion, it's between 64 and 76. When we're doing our research paper, we might go out to more decimal places. But if you're just going to say something to somebody, most of the time you just round it off to the whole percent. Okay. Do I actually know the proportion of Western students that have played Yahtzee? No, I don't. Is it 70%? No, it's not. 70% is what I got from the sample. What is the actual value of all the Western students? It's somewhere between 64 and 76%. Now, if I'm selling Yahtzee themed t-shirts at Western, is that good information for me to know? Yeah, it would be really good for me to know, hey, I've got a lot of people that have played Yahtzee in the past, they understand it, and so maybe I can sell a few t-shirts. I don't know the exact number. Even though I got 70%, that's not the actual number for the population. But at least I have, from my sample, enough information to know there's a heck of a lot of people that have played Yahtzee and know something about it. But I had to have talked to 200 people, and that's not easy to get 200 people, but I could do it. So when I have a sample like this, it's not telling me what the population number is. But by going through this process, I know with 95% confidence that that population number is somewhere between 64 and 76%, which is a pretty good thing to know if I want to market something that I've got a pretty good amount of people who know what I'm talking about. Okay. What happens, though, if I change my level of confidence? I now am going to say, what about a 99% confidence interval? Not a 95%. I want a 99%. So it's going to change. The question is, how much is it going to change?
We're doing the same thing except with 99.
We're doing the same thing, except now we're going to do with 99% confidence, or a 99% confidence. For the proportion, the population proportion. What do I need to change? I need to change my z-score. My z-score will be different. My alpha is the same. I don't know, my alpha's not the same. I want 99% confidence. So what's alpha?
0.0.
Alpha will be 0.01. What's alpha divided by 2? If I take 0.01 and I divide it by 2, what happens? 0.005. Now I need to find that z-score.
Which one would you choose?
Shouldn't 0.005 be alpha divided by 2 equals that? Not just alpha.
Oh, thank you.
Is it 0.00 or negative 2.5? That means
It could be. What else could it be?
Negative 2.58.
7. Negative 2.
Negative 2.58 or negative 2.57 are pretty close, right?
5 is closer.
Would you divide them?
They're actually the same distance away, so does it matter? Not really. Okay. But if we're going to say what we would use, we could go with negative 2.575. We go right in between the two. Okay. So the z for this alpha over 2, 2.575. Now, the textbook publishers are hopefully smart enough to be able to accept either one of those answers or this one. Okay. For right now, we're going to go right in between.
So are all the other numbers the same then?
Yes.
Yeah.
Yeah.
Question. I'm sorry, what?
Where'd you get the 2.5?
When I looked on the z-score chart, it was between negative 2.57 and negative 2.58. So if we split the difference, it's negative 2.575. And then when we're putting it into the formula, we just put the positive value in here because it already has a negative and a positive sign. Does that answer your question? Okay, if we were to say, where does this come from? We have to look up this number on the z-score table. And that has to be the area number on the inside of the table. All right, there we go.
I know.
Please plug it in. That's right here. That's where it would go. Yeah. Now it's 2.5. Everything.
Yes. Negative 2.57. This one, and then you put the number in.
Okay, I just looked at the textbook question for the online homework, and they use 2.58. So that'd be all right.
find the z-score on the chart, we just automatically make it a positive number, even if the answer is a negative number?
Yes.
Like they ask you what is the z-score, even though it's negative, it's 2 point whatever, we would say positive.
Okay, when they ask the question, what's the z-score? That doesn't really matter. They're going to ask the question, what's the confidence interval?
Okay.
All right, so once again, if we go to 3 decimal places for this, we're going to go with 617 and 783. So that means it's going to be between 62 and 78. So what happened here?
Yeah, bigger.
It got bigger. We are more confident about the result, but that made it just a little bit less accurate. Okay, so now we say, oh, it's between 62 and 78. Before we said 64 and 76. Well, we're trading off confidence for accuracy. We're more confident, we're more sure about the result, but we don't know the number as much as we did before. So if we try to be completely sure, then we would not really know what the number was. But we're adjusting our confidence, and that changes the accuracy. Is this a big change in accuracy? Not really. Okay. Most of the time, we'll just stick with 95% confidence, and that'll be close enough for us to be able to get a reasonable amount of accuracy for what we want, hopefully. Now, what happens next is that we're going to change our sample size. We're going to say, let's do the same kind of a problem, and let's go back to our 95%. But we're going to change our numbers. So p hat is going to be, let's say, we'll go by a factor of 10, 20, maybe 25. So yeah, let's say it's 3,500 over 5,000. Okay. So 3,500 divided by 5,000 is still 0.7, so Q hat is still 0.3. But what's N? 5,000. And we want the 95% confidence interval. So that means our z-score is going to be 1.96. We already know that. Okay, better check your neighbors, see if they're doing it right.
This is right. This one's not. Plus one times, and then your square root. And then you got this year's result. And then parentheses. There you go. Same as right. This is right. This is right. Nope.
All right, so I've got 687 to 713. So it's between 69% and 71. Okay, so what happened here? Okay, it got smaller, which means that if we have a large sample size, we have a more accurate understanding of what's going to happen. Well, if we change to 99%, it wouldn't be that much different. Okay. So what happens here is that if you're able to get a very large number of people who are in a particular category, and you can ask them a question, then you've got a pretty decent sense of everybody in the category, no matter what it is. Because if you have a large sample, if it's random enough sample, okay, you're not just picking, all the scientists out of the group and you got 5,000 scientists, well then that's not random now, is it? But if you're able to have a random sample that's large, then that means you're able to have confidence about your results. If you only have a small group of people, then you're not going to get a very accurate representation. There's too much variation in that. But if you have a large sample, then you're more sure about what's going to happen. This is why when they do trials of drugs or medications or treatments, they'll have 10, 20,000 people who do a thing. Because the next time they do it, they're going to be putting it out to millions of people, and they want to have some idea what's going to happen. So you can't usually go from just a couple hundred people to know what millions of people are going to do. So then you go up to tens of thousands, then you get a decent shot at least knowing what's actually going to happen pretty accurately. And then when you go to the millions, you'll have even more. All right. We'll move on to our next thing after our break. So we'll come back to 427 and go to the next.
There it is.
Here's the thing. Yeah.
What?